All right. Hello, everyone who's watching this online. I'm David. I'm the coordinator of the Maths Learning Centre. This is a revision seminar for Foundations of Maths for Data Science, possibly Math Foundations for Data Science in semester 1 of 2021. I've got a few students here who've got some questions that we're going to talk about. And the first thing that's come up that has been possible to actually look up is Fermi estimation. And what we've said so far, I've already talked to these people about it already, but I just wanted to pass on to you who are watching online in the future, what we've said so far, which is that Fermi estimation is named after, I think, a physicist, Fermi, who used to practice doing calculations this way. And the idea of it is to be able to explain your process of coming up with your estimate for a particular number. And I think, and we all seem to agree, that the people who run this course are nice sorts of people, and they're not going to penalise you for having an answer that's a lot different to the answer they were thinking of. And also, I think they're going to be a bit friendly and try and choose things where the general knowledge, and they might tell you some useful things like the population of Australia or Adelaide, but even if they don't, then I think it's okay for you to just pick random numbers and run with them, because they're trying to assess your reasoning skills, not so much the final answer. So that's the general idea, that we can make us feel a little better about trying to do these in the exam if they turned up in the exam. I'm not sure if they'll do it in the exam. I feel like this is the sort of thing that would be much more reasonable to talk about in a tutorial than in an exam situation. But we're going to talk about it anyway, just to be sure we've got the general idea. And I'm going to do it possibly wrongly, but the idea is to see what I think might be reasonable for them to mark it with. So one of the examples in the course was estimate the number of people in Australia looking at their phone right now. So for me right now is about 2:30 p.m. just doing, and the population of Australia, I have no idea. It's between 20 and 30,000. I'm just going to make a guess, 30,000 approximately. And it seems to me that to be looking at your phone, you should own a mobile phone. And I'm going to have to make a guess at how many people own a mobile phone. I have absolutely no idea. Almost every adult that I meet has one, even my father-in-law, who is 75. So I would argue that almost all the adults have one. I don't know how many of those 30,000 people are children. I'm going to make a guess that maybe 60% of them are adults. And so which is whatever it is. 10% of 30,000 would be 3,000, and 6 times that would be, so that's approximately 20,000, million, not 30,000, 30 million. All right, about 18 million adults. And most adults that I meet have mobile phones, so I'm going to say but I guess a whole lot of kids. So maybe we don't want adults or teens. So maybe I'll bump that up to 80% of them are adults or teens. Most adults have phones. And so I'm just going to say maybe 90% of people have phones. And so the number with phones is 90% of the 24 million. And 90% of 20 would be 18. And 90% of 4 would be 3.6. So we're looking at approximately 20 million. And so now we need to estimate how many are looking at their phone at this exact moment. I don't know. I guess you could make a guess at what percentage of your day you spend looking at your phone. I just have to make a guess. I have no idea what's reasonable. So I'm going to guess. Actually, I can't look up my phone because I'm in an exam. So my phone tells me how many hours a day I spend looking at my phone. I don't know if that's small or big. So maybe I spend like a couple of hours a day. So 2 out of, but I don't spend the night. So 2 out of the daytime hours looking. So that's approximately 2 out of, say, 12 hours of daylight, right? 1/6 of the time. And so I'm guessing that 1/6 of the people are currently looking at their phone. And a sixth of 21 million. Well, 18 would be 3 million, and a sixth of 2 is 2/6, which is a third. So we're looking at about 3 million-ish. That's how I would do a Fermi estimation for this problem. This squiggly equals is an approximately equal to sign, by the way, in case you've never seen it. Does this feel like Fermi estimation to you? So the point I want to make is that each step in this, I have written down what my assumption is. And I've told I've written down when it's a guess and when it's something that I actually know. And so I've been very clear about what a guess is. And then I've also done this. So I feel like this would be an acceptable answer in the exam, even if the number is totally different to the number they were thinking of. Because I mean, the actual population of Australia, I think, is 25 million, but honestly, whatever. If you don't know the population of Australia, then you just guess a number. And if you're overshot, if you say it's 300 million, which is close to the population of the USA, then all right, well, we'll get 30 million here. Like we'll get 300 million, not 3 million, 300. We'll get 30 million here, and that's just what'll happen because it's based on the assumption you've got, and there's nothing you can do about it. And I don't think they will take marks off for that. But since they often tend to be about population, some useful general knowledge facts. The population of Australia is about 25 million, and the population of Adelaide is about 1 million. Just if that helps for any future things. And the population of the world, what are we? Are we up to 8 billion yet, or are we still in the 7 billions? I think we haven't cracked 7.5 billion yet. So these are useful general knowledge things about populations that are not the worst things to know, just for future reference. wouldn't be the worst thing to do to look some things up. Are you allowed to have notes on paper that you're allowed to look at? Yeah, it wouldn't be the worst thing to do to write down some general knowledge things that are worth knowing, just so you can refer to them if you need to. Yeah. How do you feel about that? Okay. I have great trouble even thinking of Fermi estimation problems. Yeah. Yeah. They tend to be in the flavour of things about populations, but I was told another example was about the amount of water produced in a rainstorm or something. Yeah. So if I wanted to estimate the amount of water produced in you know, an 8-hour storm in Adelaide, I'd have to know how much water I expect to come down, and probably the area of Adelaide. So let me do another one. I mean, I don't know, it could be anything, right? So we're just going to have to choose things. Area, the volume of water produced in a one-night thunderstorm. I'm going, okay, so the time of the thunderstorm looks like it's about, I mean, when I say one night, it's probably not 12 hours. So I'm just going to go like 9 hours. And that might not actually be relevant, because I know that when they talk about the amount of water that's produced in a storm, they talk about the number of millimeters. So, you know, rain is normally measured in millimeters. And they'd normally say a big storm would be a good, I don't know, 4 millimeters or something, possibly even 10. That's my guess, because I know that the rain they did the other day was only like 1 millimeter, and it was not a very big, it was quite a big storm. So let's just say rain in millimeters, don't need that. Let's say it was 20 millimeters, which is a big storm. So I'm not going to worry about the hours. I'm just going to think about what I've seen about reports of rain time, but you could guess whatever you want. You could also guess the rain per minute if you wanted to. I'm just going to say it's a 20 millimeter rainstorm. And then I'd need the area, that's the depth, and so I'd need the area of Adelaide, because that's where I live, so I'm going to do that. All right. I have no idea. I know that it takes me about 30 kilometres to get to work from Gawler, so maybe it's 60 kilometres wide this way and 60 kilometres wide this way. So maybe the area is 60 by 60 kilometres. And so the total amount of rain should be 3,600 kilometres squared times 20 millilitres deep. So I'd need that in meters, wouldn't I? Let me just do it all at once. So 60 kilometres is 6,000 meters. And so the area is 1,000 squared meters squared. 1, 2, 3, 4. So that's 10 to the power of 4, and when I square it, I get 10 to the power of 8 meters squared. And the depth is 20 millimeters, which is 0.02 meters, because a millimeter is a thousandth of a meter. And so the volume is 36 times 0.02. 36 times 2 would be 72. All right, that's how many meters cubed it is. I should probably put the working in, 0.02 times 36 times 10 to the 8. And so we're looking at approximately 1 times 10 to the 8 meters cubed. And a meter cubed is a megaliter, so that much water. But I mean, this was based on an estimate of a rainstorm producing 20 millimeters straight up. I don't know. I could have tried it a different way and done how much how much depth does it produce in a certain amount of time for an area. So I could have imagined in my rainstorm having a glass of water out there and thinking, or I could imagine a glass of water in the rain and imagining how long it would take to fill that up. And thinking, well, if there's a big rainstorm, maybe, or what if I was in the shower? I reckon that'd only take like 5 minutes to fill up that. To fill 250 milliliters. And so in 9 hours, in the 9-hour storm, we'll get, so 5 minutes for 250 milliliters, 10 minutes, 20 minutes would be an entire liter. And so 1 hour would be 3 liters. And so a 9-hour storm would produce, a 9-hour storm would produce 9 times 3 liters, which is 18 liters of water in the area that my cup takes up. So I imagine a cup. And so the area that my cup takes up is about this big. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I don't know, 20 square centimeters. Well, maybe just a second. If it was a square cup that was about this big, that's 5 by 5, 25. But no, 20 is not too bad then, is it? And so I need to figure out the total area of Adelaide and how many cup areas that's worth. And so I would copy my working for the other one, which was I need it in centimeters squared, don't I? So it would actually be 60, another 100. And so that would be 36 times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so the number of cup that is this divided by 20, which is 18 times, so the 36 divided by the 2 would be 18, and the 10 to the 12 divided by the 10 would be the 11. And so the total volume would be 18 litres times 18 times 10 to the 11 cups, which is however many litres it is. So what? 18 is nearly 20. So 20 times 20 would be 400, which would be 4 times 10 to the 13 litres, which would be 4 times 10 to the 10 megalitres, because a megalitre is worth 1,000, which is not too bad. It's quite a lot more than my other estimate, but there you go. It doesn't really matter. The point is that you just make an estimate, and you making choices about how you're going to over or underestimate things is perfectly reasonable. How do we feel? It seems to me that they're just going to be nice about it in the exam if they ask you one. Just have to be clear about your reasoning. Okay. So I've had a specific request here. Solve one question for conditional probability and list the formulas required for that. Do you have a specific example? Because I don't have access to the My Uni course. If you had a problem that was bothering you that contained the sorts of things you want to do, that would be really useful for me to help you do that. I'm just going to pause the recording for a second while you search for that. Okay, so one of the students has given me a conditional probability problem, and we'll work through it and we'll talk through some of the issues that happened. Okay. Suppose a pest control program dealing with two types of rats, black and brown. It is found that one of the rats they have caught in the traps so when a rat is caught in the trap, the probability of it being brown is 0.2. Okay. It is estimated that the probability of any rat being caught is 0.5. And that the probability of a randomly chosen rat in the region being brown is 0.9. I'm just going to call it a wild rat instead of a rat in the region. .9. What is the probability of a brown rat being caught in a trap during this time? Okay, that's a lot of information. Thank you very much for giving me that. Okay, so this is an example. So there's a lot of information here and I need to pull this apart. And in success with conditional probability is figuring out the situation or object that has information recorded about it and the information that's actually, and how that information is related to each other. So it seems to me that we're interested in the probability of a brown rat being caught in a trap, and the story that produces that is that first you've got a rat and it's either black or brown, and then it gets caught. And so that's my understanding of the story. So you get a random rat, which is either black or brown, and then it gets caught or it doesn't get caught. That's my story. And so I'm going to draw that story, all the possible stories in the tree diagram. So a random rat comes along. So this is the story I'm imagining. There's my rat. Here's my trap. This is not, it's not necessary to draw the pictures to be part of, to do your thing. Here's my trap. And then a rat comes along. And either it's caught in the trap or it gets away. Okay, that's my story. So I'm thinking that we choose our rat and it's either black or brown. That's the first stage in my story. So at the moment there's two possible stories that could be told. The rat that came along to my trap was black, or the rat that came along to my trap was brown. And then afterwards it's either caught or it's not caught. So this is the story. A black rat comes along and it gets caught, or a black rat comes along and it doesn't get caught. A brown rat comes along and it gets caught, or a brown rat comes along and it doesn't get caught. Okay, so it says that the probability of a random rat being brown is 0.9. And so I'm going to put that probability here. And the probability of a random rat being black must be 0.1. So I'm just going to write that as my working. That's this part here. And then the probability that the rat gets caught is 0.5, it says. And so that means the probability that doesn't get caught is also 0.5. Oh, crap, just a second. I've done something wrong. Oh. So the reason I think I've done something wrong is that this probability here says to me that this is the probability of a rat being brown given that it has gotten caught in the trap. That's what this says. And that this is the probability that the rat has been caught at all. And this is probably that a random rat is being brown. So I'm just going to write that information down and try and get my story straight. And the probability that the rat is brown, given that it's caught, is 0.2. Okay. The grammar of this is difficult for me to process, but this is definitely true. It says that when a rat is caught in the trap, the probability that it's brown after you've got the information that it's caught is 0.2. So it seems to me this statement here of what is the probability of a brown rat being caught in the trap, that seems to me that it could be interpreted as what's the probability of the rat being brown knowing that it's caught in the trap? And that would be just 0.2, which we already have. So they must mean what's the probability of a random rat being caught if it's a brown rat. That's what they've asked me to do. So when I look at my story here, this isn't 0.5 here. This is a question that I don't know what the answer to is yet. But I do know the answer to this question, which is the total probability of getting caught. Okay. I'm going to see if I can figure this out. So Bayes' theorem says that the probability of getting caught, given that the rat is brown, would be the probability of getting caught and being brown divided by the probability of being brown. And we do have that probability, and this one we don't know yet, but this should be, I can get that probability by imagining it first being caught and then being brown. So this will be the probability of being caught times the probability of being brown given that it's caught. Like that. And this is Bayes' law. And so the probability of being caught is 0.5, and the probability of being brown, given that you got caught, was 0.2, and the probability of being brown was 0.9. And so I can figure out what all of those things are. Okay. I don't like that it doesn't match with my tree diagram. I mean, it does. This is the number here. That's the number I just figured out. And it says that this probability, all of that together, of being caught at all, is together 0.5. So the other end of the story. Just getting more paper. I could have done it as a Venn diagram. Is this the correct answer? Right. So I was making it more complicated than it need to be by trying to think of the story, but I still like the story. Because it should be the probability of Court and Brown is this bit here. Yeah. So I think that this question was trying to get you to ignore the story and just look at what's written here and create the formula. Because a tree diagram doesn't have to be a time order of events. It can just be when you figured out the information, because I can draw it as a Venn diagram instead, right? So these are all situations where rats are caught in traps. And these are the situations where the rat is brown. And these are the situations where the rat gets caught. And out here are all the black rats that don't get caught. And here are all the rats that get caught. These ones are black and these ones are brown. These are all the brown rats and these ones don't get caught and these ones do. And so we're told that the probability of being caught is 50%. So half the rats are in here and half the rats are out here. And we're told the probability of being brown is 0.9. So 90% of the rats are in here and 10% are out here. And then we're told that if you get caught, out of the ones that are caught, 20% of them are brown. So this bit just here is 0.2 of the caught ones. That's what's going on in my head. And so that means it's 0.2 of the 0.5. Yeah. And I want to know, given that it's brown, how likely is it that it's caught? Well, that's this bit out of that bit. So Venn diagram might be an easier way of understanding what's going on here. Need to focus just on what's required to solve the problem and ignore the rest. Yes, I don't like giving people that advice, but it is sometimes useful advice for exams. I will say that no matter what, every probability situation that has two pieces of information, so this one has information about the rat and about whether it's caught or not, can have two tree diagrams and one Venn diagram be drawn, and you get to choose which one to do. And so I could have, this one just got me confused, so I could try it the other way around and be caught and then be black or brown. Yeah, but I think the Venn diagram was the best choice. So, yeah. So I think what's in the lecturer's head is to set up the formula and go, oh, that's all the pieces of this formula, so I'm just going to not worry about drawing a diagram of it. So I reckon your strategy is a good one. Did you have any other problems or things you wanted to talk about? Yes, please. We'll talk about whatever it is you want to talk about. So we've got another problem here. Let's write it down. Suppose the tourism board decides to look over their data on international tourists to Australia to make some predictions for when tourism resumes. They find that the probability of international tourists that an international tourist visits Adelaide if they're a wine drinker is 0.15. So the probability that an international tourist if a wine drinker is 0.15. And the probability that they visit Adelaide if not a wine drinker is 0.1. Don't know how they would know that, but anyway, it's just a random question. It is estimated that the probability of an international tourist being a wine drinker is 0.6. Okay. What is the probability that an international tourist will visit Adelaide? Okay, so that's the problem. So the story is that we have an international tourist, and they either drink wine, it's a wine glass, yes or no, and then they either visit Adelaide yes or no. Okay, that's the story. And those two bits of information create four options for what a person could do. They could either be a wine drinker and visit Adelaide, they could be a not wine drinker and not visit Adelaide, they could be a wine drinker and visit Adelaide, be a wine drinker and not visit Adelaide, not be a wine drinker and visit Adelaide, or not be a wine drinker and not visit Adelaide. There's four options. And so those four options I could arrange in one of those story tree diagrams like I did, or in a Venn diagram, or in a table, or anything I like, but I might write it down in probability notation first. The probability that an international tourist visits Adelaide if they are a wine drinker is 0.15. So the grammar of this sentence says that we've got an international tourist visit Adelaide if they are a wine drinker. And so that says to me it's a conditional probability. Given they're a wine drinker, the probability that they visit Adelaide is 0.15. And then probability that an international tourist visit Adelaide if they're not a wine drinker. Okay, so the probability that they visit Adelaide given not wine drinker is 0.1. Okay, and then the probability of being a wine drinker is 0.6. Okay, so the way this story seems to work is that I have the straight up probability of being a wine drinker, so I can imagine as that being something that happens that I know about first. And so my story can be choosing, I can imagine all the people as being wine drinkers or not, and there's all these little people that have this information about them, and I can imagine choosing the person who's a wine drinker first. And so I've got wine drinker, yes or no. And the probability of choosing the yes is 0.6, and the probability of choosing the no is 0.4. And then I could choose whether they visit Adelaide. And the reason I put this second is because my conditional probabilities have the wine drinker as the thing that we know first, and then the visit Adelaide as the thing that we know second. And so given that they're a wine drinker, that's here, the probability that they visit Adelaide is 0.15. And so the opposite probability should be 0.85. And given that they're not a wine drinker, the probability that they visit Adelaide is 0.1. So the opposite probability should be 0.9. So I should write down some of those calculations I did. I don't know if any of that's important yet, so I might just deal with it later and write them down when I get to them. So the probability, I want to know what's the probability that they do visit Adelaide. So visiting Adelaide is this part of the story and this part of the story. So it looks like I'm not going to need these numbers anyway, so I'm not going to actually write them down in my calculations. So to get, I need all the ways of visiting Adelaide. I need to figure out those probabilities separately. So first I'm going to figure out this. So the probability of not being a wine drinker is 0. Well, if I'm going to do the full calculation, it should be 1 minus the probability of being a wine drinker, which would be 1 minus 0.6, which is 0.4. Okay, so this story here is the probability of visiting Adelaide and also being a wine drinker. So this is not given that you're a wine drinker, it's just randomly picking a person who happens to both visit Adelaide and be a wine drinker. And this should be first the probability of being a wine drinker, then the probability of visiting Adelaide given that you're a wine drinker, which will be 0.6 here times 0.15 there. Okay. 6 times 10 would be 60. Six times 10 would be 60, 90. So that's, I think that's 0.9. No, 0.09. Thank you. So that's this probability here, 0.6 times 0.15, which is 0.09. And then the probability that you visit Adelaide and not be a wine drinker should be the probability that you're not a wine drinker times the probability that you visit Adelaide given that you're not a wine drinker. So not being a wine drinker is 0.4. Probably visiting Adelaide given that you're not a wine drinker would be 0.1, which would be 0.04. Just adding it to my diagram up here. And so if I combine together all the probabilities that go with arriving in Adelaide, then that's these two together. So the probability of visiting Adelaide is the probability that they visit Adelaide and they're a wine drinker, plus the probability of visiting Adelaide and not drinking wine. Which is we already figured that out. This one was 0.09 and this one was 0.04. And so the answer is 0.13. It might have been easier to write this if I had given letters to the different events. So I could have written this. Before I do that, how are you feeling? So I could have gone back and I could have written my working in a whole different way. And right at the beginning, I could have said that W be the event that the person is a wine drinker, and A be the event that they visit Adelaide. And then I could have, instead of doing visit Adelaide, I could have just put the letter A, and this could have been W, and this could have been A, and this could have been, can I ask, in your course, do you do WC or W bar for not W? All right, and then this would have been just W. And so the working would have turned out a lot simpler. This would have looked like probability of Adelaide and W is probability of W times the probability of Adelaide given W, which is whatever it is. And this would have been A, W bar, A, W bar. So the working would have been a little bit shorter at the end. This one would have been probability of A is probability of A and W plus probability of A and W bar. So you could have written it all in probability notation by right at the beginning saying a letter that stands for the name of the event. Yeah, I do really like the, if you want to look up online more information about this, lots of people call this a tree diagram. I call it a story diagram because it tells the story, but this is what it would be called if you ever want to search for information on it on the internet. You are most welcome.